Okay. Good morning, everyone. Hope you're all doing well. We're going to start by talking about, maybe you've heard of it, the tennis racket effect. So let's do a small experiment. I'm going to take my phone. I can consider it to be a rigid body, right? It's kind of rigid. What I'm going to do is that my phone is a symmetric body. I want to try to rotate it about its three principal axes. So if I have my phone, looks like this. I can write the inertia tensor. So it's just a phone. Looks like this. I can write the inertia tensor for my phone about a co-rotational axis. And if I orient the axis kind of along the axis of symmetry, my inertia tensor is going to be diagonal, right? If I orient my rotational basis along the axis of symmetry of the phone, I'm going to get a diagonal inertia matrix. So what I want to do right now is I want to rotate my phone about these three principal axes. So one of them is going to be a rotation like this. So what's going to happen if I flip my phone like this? You can try it if you have a book or something. If I give it an initial rotation like this and let it rotate, let us try to do so like this, and I let it rotate. Let us observe what happens. I'm going to try to make it straight so that it doesn't topple a lot too. I can the rotations are going to be kind of close to what I intended them to be. Let me do another different kind of rotation where I rotate my phone about this axis. What's going to happen? The rotations also are going to kind of remain how they're supposed to be. But now if I take my phone and I rotate about this axis, what's going to happen? Do the rotations remain about that axis? No, they don't. Okay, so this is what's called, have you observed this before? Maybe. This is what's called the tennis racket effect, or the Hanibikov effect. So what this says is that if I have a rigid body and it is axisymmetric, if I rotate the body about its intermediate axis of inertia, so if I have the rigid body and it has three moments of inertias, right? So I'm going to look at the Tost book. Maybe this is a better visualization of what I was trying to show. So there's this interesting extra turn that the racket does in the air. Maybe we'll look at it one more time. Oops. This interesting extra turn up in the air. So why does this happen? We're going to figure out why this happens, I'm going to take a rigid body like the phone, a rectangular parallelepiped. The same effect happens there. I'm taking a co-rotational basis that's along the axis of symmetry of the rectangle. What are the equations of motion of this system, this rectangle, when I toss it in the air? What are the forces acting on the rectangle? What is it? Yeah, just the weight acting at its center of mass. So what are the balance laws that apply here? Any constraints acting on the rectangle? No, no constraints, right? Just the weight at the center of mass. So the equations of motion are the balance of linear momentum, F equals mac, meaning that the weight is equal to the mass and acceleration of the center of mass. So what is the motion of the center of mass of this rectangle when it's tossed in the air? The motion of the center of mass. So what is it going to be? The motion of the center of mass is what exactly? It's the same as a Exactly, it's the same as the projectile, because the equation of motion of the center of mass is F equals MAC, which is F is just the weight. So that's just a projectile motion for the center of mass. Then we need the balance of angular momentum, right? What is the sum of moments acting at the center of mass of this rectangle during its motion? What is it? Exactly, there are no moments. The sum of moments is equal to 0. Why? Because the only force acting on the system is the weight that passes by the center of mass. So the moment of the weight about the center of mass is 0. So this is what is called the moment-free. It's a moment-free motion of the rigid body. M is equal to 0. So what are the equations of motion then? It's just that h dot is equal to 0. H dot c is equal to 0. What is hc? It's I omega, and h dot c, it's its derivative. Unlike the problems we've been looking at in class, this angular velocity, or the angular velocity of this shape during its motion, is it going to be fixed axis, along a fixed axis, kind of like we've been doing? No. Now, omega is going to have omega x, omega y, omega z components. So if I expand the h dot c is equal to 0, I get, well, these three equations are from F equals MAC. And these three equations are from setting the balance of angular momentum, h dot c is equal to 0. I get these three equations. So that these are three differential equations, right, in the three rotational degrees of freedom, or the three components of the angular velocity, omega 1, omega 2, omega 3. So I can solve these equations, right? You should be able to solve these in MATLAB, ODE 45, for example, or Python. So I can solve these three differential equations. What do I solve them for? So I can plug these into some MATLAB, Python. What do I solve them for? Omegas, right. So here in this case, the lambdas are the components of the inertia tensor. Here they call them lambda because they're principal components. The inertia tensor is diagonal because of how we chose our rotational basis to be along the eigenbasis of the shape. Okay, so I can solve for omega as a function of time. Omega x, omega y, omega z as a function of time. Does that give me the orientation of the shape, the rectangle, as a function of time? Actually, it doesn't. It does not. So if I want to find the orientation of the shape as a function of time, I'm going to have to introduce new terminology for the rotation angles, for example, Euler angles or quaternions. That's beyond the scope of this course, but just letting you know that in general, when I'm solving for the rotation of a body in 3D, then I'm going to need to introduce somehow a parameterization of the orientation of the body. So here for this body, these are the principal moments of inertia, which I can find from the tables, right? And from the shape, so if I look at the shape here, which moment of inertia is greater? Is it about E1, E2, or E3? E3 is greater, right? And I have the minimum moment of inertia mass distribution about E1. So these moments of inertia are ordered lambda 1 is less than lambda 2 is less than lambda 3. Make sure your neighbor is okay with this ordering of the moments of inertia. Any questions so far? And so what happens is that if I rotate about E2, the intermediate axis of rotation, that's when I'm going to see the instability. What does an instability mean? It means that I'm giving the phone or the shape an initial orientation, initial rotation, and if it's stable, the motion is stable if the motion remains close to the initial rotation I gave it. And it's unstable when it goes far away from the initial conditions that I gave it. So for those who are late, we're talking about this effect here. I take a rigid body and for example, a tennis racket, and I rotate it, and somehow there's this kind of extra rotation in the air, this effect that's happening. So that's due to the fact that when I integrate these equations of motion, where are they? Here, the balance of angular momentum. When I have initial conditions that are a rotation about the intermediate axis of rotation, then I'm going to see this effect. It's basically unstable. I was defining instability as if I give a system an initial condition, if the system remains close to that, then the system is stable. If the system doesn't, then it's unstable. For example, if I have a simple pendulum, I have an equilibrium configuration, the pendulum is straight down. Is this configuration stable? Yes. Why? Because if I release the pendulum a little bit away from this configuration, the pendulum is going to remain close to it. Okay? Versus the pendulum, if it's straight up, that's another equilibrium configuration of the pendulum, right? Technically, I can release the pendulum straight up, and if there are no disturbances, it will remain straight up. But if I perturb this equilibrium a little bit, the pendulum is going to swing and it's going to go far away from the initial location it had. So that's an instability there. So this is a way of parameterizing the rotation tensor using Euler angles beyond the scope of this class. I can take all of these equations and then I can animate the motion. So here, let us look at this. This is rotation along the minimum axis of inertia, small e1, and you can, is it small e1? What is happening? Let us repeat this. Yes, small e1, and it's mostly stable. Yes. And I think this one is a rotation along the maximum axis of inertia, E3. Also, the rotations remain close to E3. And this is a rotation about the intermediate axis of inertia, and you can see the instability there. Definitely the notion of stability and instability of equilibrium and then equilibria, and stability and instability of like steady motions, that's a whole big topic. I just wanted to introduce it here, introduce it to this effect. There was a popular video, have you heard of the Veritasium YouTube channel? There was a popular video about this effect that I linked in the notes. So just wanted to share. Any questions, any comments? Yes?
So I guess this is an argument my dad and I were going back and forth about yesterday.
Really?
When it's spinning in the air like that or tumbling, is it imparting angular momentum into the earth, or how is angular momentum actually conserved?
Angular momentum is conserved during this motion, right? Why is angular momentum conserved? Because the sum of moments, mc is 0, so h dot c is 0, so hc is constant. So this ic omega is going to remain constant throughout the motion. So there's no exchange of angular momentum between the body and the earth.
So how does the omega remain constant if it's kind of tumbling like that?
Omega is not constant.
Oh, it's the IC that's changing?
The components of the inertia tensor are going to be constant, right? But they're different. The omega components are going to change. You have omega x, omega y, omega z. And if we go back to the equations, so you have, omega 1, omega 2, omega 3, omega x, omega y, omega z. These three equations need to be satisfied. The coefficients are different. So you can think of, if I'm rotating about omega 1, if lambda 1 is minimum, then to maintain some equality, omega dot 1 is going to be greater or something like this. So the three differential equations of conservation of angular momentum are satisfied throughout the motion.
Okay, so then the actual components of omega will change as long as the I omega vector does not change?
Exactly.
Okay, thank you.
Exactly. Yes. So ideally, technically, if I were to have this motion initiated without any perturbations, everything is exactly aligned, I will not see this, this effect, the intermediate axis theorem effect. I only see the effect when I displace a little bit from this kind of stable motion. Right. So there are ways to visualize this effect. Kind of can see it here. These are kind of the motions of the system depicted on a sphere. And again, lambda 1 is the minimum axis, the minimum moment of inertia about E1, lambda 2 about E2, lambda 3 about E3. And these are kind of the trajectories of the system. So if I were to release the system here at the kind of edge, it will remain there. If I were to release it at this trajectory, rotating close to, notice that at this trajectory, omega 2, omega 3 are very small. Omega 1 is the largest. It will rotate along omega 1 mostly. Same for omega 3. Here, this trajectory, do you see my pointer? This trajectory has omega 1, omega 2 almost 0. Omega 3 is almost maximum. If I have a trajectory here, it's going to remain close to here. But notice that if I start here at a point where omega 1, omega 3 are very small and omega 2 is very high, I'm going to deviate very far from that trajectory. So this is a way to illustrate this motion. Okay, that comes from the intermediate dynamics textbook, which is usually discussed in ME 75, 175. Okay. Any questions about this? Okay. Cool. Now let's go back to our regular work. Last time we looked at problems from set 20, fixed point rotation. Today we're looking at problems from set 21, general plane motion. So motions where there is not necessarily a fixed point. So usually we're applying the balance of angular momentum either about the center of mass or about any material point P, not necessarily fixed in this system. Okay. So let us look at set 21, problem 1. Are there any extra papers in the back? I'm not going to use numbers. I'm going to introduce dimensions as such. Oh, I forgot to show you something. It's fine. Let's take the notes. Okay. So problem 661. The body consists of a uniform slender bar and a uniform disk, each of mass m/2. It rests on a smooth surface. Okay, so the surface is smooth, meaning that there is no friction between the surface and the body. Determine the angular acceleration alpha and the acceleration of the mass center of the body when a force P equals to 6 newtons is applied as shown. The value of the mass M of the entire body is 1.2 kilograms. Okay. So we have this body, M over 2, bar has mass M over 2, disk has mass M over 2, a force P is applied as shown in the figure. We want to determine the angular acceleration alpha and the acceleration of the center of mass of the body when P is applied. What do we do? Okay, determine where the center of mass is, then what? Well, yeah. Well, first I think we can determine the acceleration of the center of mass without figuring out where it is. How would we determine the acceleration of the center of mass? Yeah, F equals MAC. So if I look at the, well, let's first draw the free body diagram of the body. What are the forces acting on this body? We have the center of mass, right? And we have a weight into the page, a normal out of the page acting on the body, and the force P, right? P, P1. Okay. How do I calculate the acceleration of the center of mass? I'll use the balance of linear momentum. F equals MAC. I'll add all the forces. Any simplifications here? Yes, exactly. Why are the normal and the weight, why do they cancel out? Why do they sum to 0? Yeah, they're along EZ, right? And there's no motion along EZ, so N plus W is equal to 0. Then I get that P is equal to MAC. So the center of mass behaves like it's a particle being pushed by a force P. The center of mass behaves like it's a particle being pushed by a force P. Now I want to determine alpha, the angular acceleration of the rigid body. What do I do? Which equation contains alpha? Which equation are we going to use to find alpha? What is it? Well, this equation uses alpha. And if we have alpha, well, if we have do we have the accelerations of two different points on the rigid body? No, we only have the acceleration of the center of mass. So we don't think we're going to use this equation. We're going to use the balance law. Which balance law are we going to use to find the angular acceleration of this rigid body? The balance of angular momentum. About which point? Do we have a fixed point here? No. So that's out of the question. So we can do the balance of angular momentum about a moving point P or the center of mass. Do you have any preference here? Yeah, center of mass. No need to take any particular moving point other than the center of mass because it would complicate the equations and there's no gain to be had from that. Okay, so the balance of angular momentum about C. And that's MC is equal to H dot C, right? How do I calculate MC? You see how I'm going step by step? I decided which equation I'm going to use. I know this equation contains alpha because the H dot C part of the equation contains alpha. I wrote it down, and now I'm going to try to figure out what each term in the equation is. So first term, what is MC? The sum of moments about C. How do I calculate that? Exactly. It's the distance crossed with the force. Be careful. Okay. So it's the position vector. So I'm calculating the moment, which is the only force here that's giving a moment about the center of mass. P, right? And what is the moment of P about C? Let me call this point A. I'm going to add a few points here. B, C, D. So A is the end of the shape. B is the center of the bar. And here it's all the center of mass. Okay. So how do I calculate MC again, the moment of the force at P about C? Yeah, RA minus RC cross what? P. Okay, is equal to H dot C. One comment I want to make here is that I've seen this mistake last time on Tuesday, and if I see it in the final, you're going to lose a lot of points. If you put P cross RA minus RC, do not do that, that's wrong. The moment of a force is the position vector from where you're trying to find the moment about to the point of application of the force crossed with the force. Okay? Now H dot C, I know that omega is along EZ, right? The angular velocity is along EZ, so I can use the simplified equation, which is here. H dot C is ICXC omega dot, which is alpha, right? Yes.
Sorry, while I'm writing, out of curiosity, would you recommend us memorizing this formula, or should we?
This will be on the formula sheet. Technically, you could always write the matrix, write omega, and then get it. Differentiate and get it. Okay. So basically, here I'm using the computational basis, so I'm going to add it on the figure. EX, EY, and EZ is outside the phase, which is along the axis of rotation, so I'm fine. I always need to be careful that EZ is along the axis of rotation, which is fixed. Okay, so now this is the equation. If I fill all the terms out, I should be able to solve for alpha. What are the terms I need? So alpha here is my unknown, right? P is known. RA minus RC, do I know that? What is it? Not yet, but I can find it from geometry, right? So let us find this term from geometry. Okay, take a couple minutes, please calculate this term. RA minus RC. It should not take a lot of time. Do it in pairs, and I want to check your work. So you're finding the center of mass relative to the end A of the rigid body. Any questions? Anyone done? Yeah? Okay, so what is it? How do we do it? RA minus RC is what? Let me do RC minus RA. Yeah. It's the mass of the bar, which is m over 2, times the center of mass of the bar relative to A, which is L over 2 EX, plus the mass of the disk, which is m over 2, times the position vector of the disk relative to A, which is going to be L plus R over m over 2 plus m over 2, which is m. So it's going to be, and that's also along EX. Along EX, m over 2, 1 over 4, m, well, m cancelling out. Okay, so 1 over 4 plus 1 over 2 is what? 3 over 4. 3 over 4 L plus R over 2 EX. Right? Is that what you got? Awesome. Okay, so this is here 3L over 4. 3L over 4 plus R over 2 cross P EY. Okay. Now I need to calculate what? What do I need to do next? Yeah, I need to calculate the moments of inertia and the products of inertia. So now I need to calculate what are the products of, yes?
Sorry, a question on a test is okay if we just give to Z since we can take the dot product to show that Z component is the only thing left.
Can you repeat the question, please?
I guess if we take the dot, once we work out the thing, we show that EZ is the only component left of the left side of the equation.
Yeah.
So therefore, the only moment of inertia that matters is EZ. Should we just still do all three on a test? Or?
Yes. Here we're going to show that the products of inertia are going to be 0. So on both sides, the EX, EY components are going to be 0. For example, for the example we did on Tuesday of the other bar, then you needed the reaction moment. And if you were to just cancel out the non-EZ components, you wouldn't get a reaction moment, so you would be doing something wrong, right? So I wouldn't just cancel because everything needs to be along EZ.
Okay.
Yeah. So what are the products of inertia here? 0. They're going to be 0 because Z equals to 0 is a kind of Z equals to 0 is a plane of symmetry. So the products of inertia are going to be 0. Okay, now I need to calculate the moment of inertia, ICZZ. So these terms are just 0. So that's just ICZZ alpha easy. So I need to calculate ICZZ. Okay, take 2 minutes. Please calculate this moment of inertia. If you have any questions, let me know. So the moment of inertia of a rigid body that is composed of several rigid bodies, to calculate the moment of inertia of a rigid body composed of several rigid bodies, I just add the moment of inertia of each. How did you calculate the moment of inertia?
This is the rod
Mm-hmm.
plus the distance squared. This is the flat disk plus the distance squared.
That's the distance.
From
Okay.
the center of mass.
Right. Here, it's supposed to be L plus R minus. Okay, good.
For this type of problem, because the displacement is 0, that's why there's no IXZ and IYZ.
And not displacement, it's because, yeah, so when you're integrating xz to calculate IC xz, because x equals to 0 kind of is a plane of symmetry, for every point with coordinate x, you have xz and you have another point with coordinate x minus z. Or you can use the parallel axis theorem to see that. And the parallel axis theorem, AZ is going to be 0 for both. And then about the center of mass, they're also 0. Okay, so the moment of inertia of the body is ICZZ of the bar plus ICZZ of the disk. How come I can add the moments of inertia like this? Yes. Integrals, exactly. So remember the original formula to calculate ICZZ, that was the integral over the body of x squared plus y squared dm, right? Integral over a body, and I can divide that integral into the integral over two bodies. Body 1 of x squared plus y squared dm, body 1 which is like the bar, plus the integral over the rod of x squared plus y squared dm. Okay? So ICZZ is ICZZ of the bar plus ICZZ of the disk. Now, can I find these moments of inertia in the tables? Really? The moment of inertia of the bar about C which is at this distance from the end of this bar. Yes, I cannot find these values in the table. I will need to use the parallel axis theorem. So IC ZZ of the bar is equal to the moment of inertia of the bar about its own center of mass, which is B, plus the parallel axis theorem M over 2 A x squared plus A y squared of the rod, of the bar. What is the moment of inertia of the bar about its own center of mass? This you can find in the tables. 112. Be careful, the mass of the bar is m over 2 L squared plus m over 2 what are AX and AY? These are the components of the vector from where to where? B and C, right? B to C or C to B does not matter because we're squaring the components. So this vector between B and C, does it have any AY components? Any Y components? No. What about its Z component? What is it? Sorry, X component. So what is the X component? Yeah. So it's gonna be this minus L over 2. Right? Three over 4L plus R over 2 minus L over 2 squared. That's AX. So from here we can calculate the moment of inertia of the bar about its center. Double check with your neighbor that you understand this. If you have any questions, let me know, and then do the same for the disk. Any questions?
Yeah, yeah. This one you read from the sheet. This is from the it's on your
Any questions? Done? Yeah? Just one more minute and we'll finish it up. We can start with the next question. Okay, so what do I do? How do I calculate ICZZ of the disk? The moment of inertia of the disk about the center of mass of the system. What do I do here? Can I find this in the tables? No, I'm going to need to use the parallel axis theorem. So that's the moment of inertia of the disk about its own center of mass, which is D, plus m over 2 So what's the moment of inertia of the disk about its own center of mass, about an axis passing by it, 1/2? Okay, AY is also 0 here. What about AX? What is AX equal to? What is it? Right, which is what is the distance from A to D? L plus R minus the yes, and that's it. Okay, so you can do all the calculations, you'll get a differential equation for motion here. ICZZ, if I go back here, at the instant considered initially, EX and EY, small EX is equal to big EX, so I can get the equation of motion by dotting this with easy. Where ICZZ is what we just calculated. It's the sum of these two terms. Makes sense? Any questions? this is a very typical problem you might encounter in the exam. Okay. Questions, questions, questions?
Is the sign correct for the relative position of A and C? Because up there you have C relative to A, but it's A relative to C.
It doesn't matter because you're squaring. So,
Not for the moment.
oh, here. Yes, you're right. So I need a negative sign. Yes, thank you. And it makes sense that my angular acceleration alpha is going to be along negative EC. It's going to be negative. Okay. Any other questions? Let's look at the next problem. We're not doing it because it's a difficult problem per se, but just to look at the effect of the mass distribution of a rolling body. Determine the angular acceleration of each of the two wheels as they roll without slipping down the inclines. For wheel A, investigate the case where the mass of the rim and spokes is negligible and the mass of the bar is concentrated along its center line. For wheel B, assume that the thickness of the rim is negligible compared with its radius so that all the mass is concentrated in the rim. Also specify the minimum coefficient of static friction US required to prevent each wheel from slipping. Okay, so determine the angular acceleration of each of the two wheels as they roll without slipping down the incline. For A, all the mass is concentrated at the center. The rim and the spokes have negligible mass. For B, all the mass is negligible at the very thin rim. So if we were to raise these two cylinders, which would win the race, A and B? If we were to release them from rest on an incline, which cylinder would win the race? A. Why A? Smaller moment of inertia, right? Because all the mass is concentrated at the axis of rotation, so it has less resistance to rotation, right? So it's going to be faster. Okay. But how do we solve this problem? Take a minute, come up with a strategy while I erase and draw it on the board. How do we start solving this problem? Maybe it's a good idea to draw the free body diagram. I'm going to call the angle of the incline beta. Can anyone guess why I'm taking Ex and Ey along the incline and not along the vertical and horizontal? What is it? Why? Why is it? Yeah, but also all the forces are going to be like the normal, the friction, they're all going to be along the incline and perpendicular to it. So it's just the weight that is along the vertical, which we can express along the current Ex and Ey. Okay? So between the two systems, what's the only difference? What is I CZZ for an A? What is the moment of inertia of disk A about its own center of mass? It's going to be 0 because all the mass is concentrated at the z-axis, passing by the center of mass, right? So that's 0. Whereas in B, what is ICZZ? In B, all the mass is concentrated at the rim. So what is ICZZ for B? What is it? mr squared, right? It's the simplest possible moment of inertia. All the points are equidistant from the center of mass, mr squared. So it's exactly the same problem. The only difference is going to be the ICCZ value in A and B. Okay, what do I do next? I want to solve for the angular acceleration alpha first of the wheels. What do I do? Balance of angular momentum. Okay, let me draw the free body diagram first, right? What are the forces acting on the disk? Weight, normal, and friction. So the normal is NEY. Weight is going to be equal to mg minus beta AY am I right? Am I making a mistake here? Yes. Can anyone explain why ICCZ in A is 0? That's a good question. Why is the moment of inertia about, in part A, where the mass is concentrated above the center of mass, why is it 0? Yeah. So, do you want to say too? Yep.
Like in all the inertia formulas, it's like 1/2 times L squared, but that L is going to be 0 if you're already on the center of mass, like where all mass is concentrated.
Yes, exactly. You're looking at the mass distribution. So this is the bar, right? This is the system in A. And I want to look at the mass distribution of this bar about this axis. But all the mass of the bar is very close to that axis, right? If I were to look at the moment of inertia about here, then here I have a non-zero mass distribution about this axis. But about this axis, it's 0. So that's what's happening. In A, I'm rotating about this axis, and all the mass is concentrated about this axis. So if you were to apply the formula, the integral of x squared plus y squared dm x squared plus y squared is 0. Great. Any other questions? Questions? What do I do next? What was our plan? What do we do? Help. Balance of linear momentum, that's going to be F equals NAC. But I want to find alpha, so the balance of linear momentum, F is equal to MAC. This will give us NEY plus FFEX. What kind of friction force do I have here? Is it static or kinetic? Why? Why is it static? I know the direction of AC. It's going to be along the axis. So here I have one unknown, two unknowns, three unknowns. So 3 unknowns, but one vector equation in the plane, so 2 scalar equations. So I need, this equation is not enough to solve for these 3 unknowns, right? This vector equation in the plane is 2 scalar equations. It's not enough to solve for the 3 scalar unknowns. So what do I do? What is it? Balance of angular momentum. Now, balance of angular momentum about which point? I have options, right? I can do about the center of mass. What about other options? What? I can calculate MC is equal to H dot C. What is my other option? Yes, I can calculate the balance of angular momentum about P, which is the contact point of the disk and the ground. P. Any advantage for calculating the balance of angular momentum about P? The acceleration of P is not zero, so I will not consider it to be a fixed point. But the advantage there is that what is the moment of the unknown forces, normal and friction, about P? The moment of those forces about P is what? Zero, because they're applied at P. So let us do the balance of angular momentum about P, and P is equal to H dot C. I have the extra terms because P doesn't have zero acceleration. It's not a material fixed point on the rigid body. RC minus RP plus MAC. Okay. By the way, this doesn't mean that I couldn't have used that. I could have used MC is equal to H dot C. I should obtain the same answer. Not sure if I'll need more steps or not. Okay. So what is the sum of moments about P? You see, I set my equation. Now I need to figure out what all the terms are. So the first term is MP, sum of moments about P. What is that? How many forces give moments about P? Weight, the weight. So I'll call that, what is the moment of P? What is the moment of the weight about P? RC minus RP plus the weight. So that's, what is RC minus RP? That's going to be REY. The weight, which is minus mg cosine beta EY plus sine beta EX. Okay, RC minus RP is the same REY. No, I forgot the H dot C. So here the products of inertia are zero also, symmetries. So H dot C is going to be ICZZ alpha EZ plus RC minus RP is REY crossed with MAC EX. So ICZZ alpha AZ if ICZZ is 0, then ICZZ is 0. So you can replace ICZZ by whatever its value is, 0 or mr squared. Right? I'm not dividing by 0. I'm not dividing by ICZZ, so I don't have a problem. Yes, good question, because I still have two unknowns here, which are alpha and AC. So now I have, how many equations total do I have? Not 4. Because this last equation is just going to be along EZ, right? So one scalar equation, the other one is 2. So 3 equations and 4 unknowns, N, friction, alpha, and AC, so 4 unknowns. So I need one more equation. I need one more equation. What is it? Yes, and specifically which one? If you read the given, what is this ball doing? It's rolling without slipping, right? So what does that mean? What does it mean? How can I use this information that the disk is rolling without slipping? Yeah. What is the velocity of point P? Yeah. So then what? Yes. Mm-hmm.
Are we not able to just use the definition of friction to remove the...
What is the definition of friction?
Oh, because it's static.
Right, exactly. You cannot say that friction is mu k and v real over v real because it's not kinetic. It's a static, so it's still an unknown. So you cannot do that. Friction is an unknown, but what's known is the motion. You have this roll without slip condition. Vp is equal to 0. How do I use that to continue? Exactly. Vc minus Vp is omega cross Rc minus Rp. What is Ez cross Ey? Ez cross Ey, negative Ex. So that's Vc. Only point on the disk that's going in rectilinear motion. So I can take the derivative of this. AC is equal to minus R theta double dot Ex. Or AC is equal to minus R alpha when projected dot Ez. So that's my fourth equation. But they're actually, so I can just use this equation 1, this equation 2, when I dot it with Ez, this equation 2, and I would just solve for alpha and AC. I don't have to solve for the normal and the friction force if I want to calculate alpha. Does that make sense? Any questions? Yes.
So could you go over the second part of the equation earlier on the balance of angular momentum that you got RE by cross EX?
Yeah. What about it?
Oh, that's just from the
Yeah, because we're writing the balance of angular momentum about the moving point P, so you have these extra terms. H dot C is the same. The products of inertia are 0. So you have ICZZ alpha AC.
Is that called the transport theorem or is that something else?
No.
Just learning about the extra things.
The RC minus RP. We derived these when we were showing the equivalence of the equations of motion.
Yeah.
So you could have done MP is equal to H dot P plus some other terms, or H dot C plus some other terms. I feel like H dot C is always easier.
Yeah.
Okay. Does that answer your question? Okay. We're not done yet with this problem. We need to find the coefficient of friction mu s, the minimum coefficient of friction, so that you don't have slip. But how do we do that? So again, we're not done. We need to can find the coefficient of friction, the minimum coefficient of friction, so that you don't have slip, so that the disk actually rolls without slipping. So how do we do that? So how do we find mu s so that the disk rolls without slipping? What are we going to do?
If you find like FF, then we know the normal force, and so we can use the inequality to find the minimum.
Right. Which inequality are you referring to? Exactly, the static friction criterion, that the friction force is less than mu s n. We have all the equations we need to calculate the friction force and the normal force. So using this inequality, you can find a minimum value for mu s. Make sense? That's it. Okay? So I think we're done with this problem. Yes?
If you go back to using this, instead of using point P,
Yes.
use center of mass.
Yes. Yes.
Since IZZ is 0, doesn't that imply that the friction force becomes like 0? Because the only moment around the center of mass is caused by the friction force, right?
Okay, let us see. So MC is equal to H dot C. Okay, what is the only force that's giving a moment about the center of mass? It's the friction force, right? So that's going to give us that RP minus RC cross the friction force, EX, is equal to H dot C, which is ICZZ alpha EZ. So yeah, in the case where ICZZ is 0, you get the friction force equal to 0.
How does that make sense?
It'll just never slip. Because it has no inertia.
What is the friction force acting on this? What is the friction force acting on this if you're rolling without slipping? Roll without slip on a horizontal plane. What is the friction force acting? Constant angular velocity. Also. So it's a similar case. It is possible for a body to roll without slip while having 0 friction force in some specific situations. We know this is not very physical, the system they were describing, right? But you can construct systems where it is. So here when the angular velocity is constant, the friction force is going to be 0 because angular velocity is constant. The friction force is equal to h dot, which is I alpha, but alpha is 0, so the friction force needs to be 0. The friction force, which being the only force giving a moment about this point. Okay. Any other questions? So let us think. Is it the next problem? Where did I put myself? Or the next problem? The solid homogeneous cylinder is released from rest of the ramp. Determine the acceleration of the mass center G and the friction force related by the ramp. Okay, so we're gonna, the remaining 2 problems, this is gonna be a quiz. We're gonna grade 1 of them, not 2 of them. So that's what we're gonna do for the rest of the lecture. Let me think 1 second. Yeah. That's our plan. So do problems 3 and 4. If you have any questions, let me know. You're going to submit them both, and we're going to grade 1 of them. I'm going to set up the assignment.